exponential growth and decay. You might have already done a little bit with at some point in time. First thing we're going to talk about is this idea called uninhibited growth. And what's up there now is just the equation or the model for something that works like this. A equals A sub naught times E to the KT power. In the case of uninhibited growth, K is greater than 0. Now later on when we talk about decay, it's going to be the other way around. K is going to be less than 0. I think that's kind of easy to remember. If something's growing, what's going to be bigger than 0? It's going up. If it's less than 0, it's going down. Any idea what that word uninhibited means? What about like if I inhibit something? Any idea what that would mean? All right. Uninhibited just kind of means it's going to keep increasing without bounds, which is a fairly unrealistic idea for a lot of things. But that would be like when we talk about cell growth. Well, if there were no limitations, if the cells could just continue to grow, as in there were no restrictions on the amount of space they could take up, resources, all those kinds of things. So this is a model not taking those things into consideration. The first thing that we're going to talk about is bacteria growth. Example 1, bacteria growth. The number n of bacteria present in a culture time t in hours obeys the laws of uninhibited growth. And there is the formula for this particular case. N of t is equal to 1,000 times e to the 0.01 t power. So in this case, I'm giving you the model off the bat. Now on our next one, we're actually going to come up with a model by ourselves. That would be the more useful part. That would be like if you did some kind of science experiment, you could figure out how many you had to begin with and how many you had later. We're going to use that info to write the equation. So right now, we're going to act like somebody else has already done it. They've already done a study. They know for this particular bacteria, this is the model. So we're going to answer a few questions. First one. What is the initial amount of bacteria? What is the initial amount of bacteria? Looking at it, can you figure out what that's going to be? Well, there's a couple ways to figure it out. If we're at the initial amount, what's our time going to be? 0, because that's right when we start. So we're just going to look at n of 0 is going to equal 1,000 times e to the 0.01 times 0 power. It would just be 1, because we're going to take e to the 0, just becomes 1, so it is 1,000. So what we know now to begin with, whenever this bacteria started, when the sample was initially taken, there were exactly 1,000. Okay? In ways that like a scientist would figure that out, if they had some kind of petri dish, they weighed it. There's data about how much the bacteria weighs, so they figure out the weight, do some calculations, figure out that's how many there are in the sample. Okay? So that's one question we can figure out. What we're always going to see, that initial amount is going to be that number there. That's what that n sub naught stands for. E is your initial amount. So you don't have to do that calculation because it's always going to work out. When you plug in 0, that part's going to cancel out. So whatever's in front is your initial. Okay. Next question we're going to answer is, what is the growth rate? So there's another one, we can just look at this. What is the growth rate of this bacteria? 0.01, so what percent? 1%. And then 1%, probably add to it per hour. We were told our T was in hours. So every hour, that's what's happening. Part C, want us to graph the model. Okay. This we can completely do on our graphing calculator. So grab those, go to your y equals, and then just type in the initial part of this. 1,000, get our E key, 0.01. Our variable is the T, so you can just use your X there. So instead of T, just use your X key, and then close parentheses. Graph. All right, you coming up with it? Go ahead and play with your windows some. Because what I can tell initially on this, the first point is 0, 1,000, so it is way up there on the y-axis. So what I hit, I went to zoom, and I went to zoom fit, the very last option. Just what's here. So what's going in on mine is exactly 1,000. And then I hit the E key. So E, and it's showing me the caret, parenthesis, 0.01, then X. That's what I've got typed in mine. Okay. So after I've got that graph, everybody do the zoom fit, 10th option. So you should be seeing something that's kind of like this. And again, I just kind of expect a sketch here. What I'm seeing, it does show me over here, and then it kind of goes up like that. Now, we really don't care about what's on the left. There's a little bit of curve to it, and it's kind of hard to tell because those numbers are pretty close together, but there is some curve to it. I did kind of exaggerate a little bit when I drew it out, but it is there. But yeah, if you're seeing a straight line or something that looks like a straight line, you probably still do it right. As close as that is, the calculator didn't really do a pretty good job of graphing it. Okay, let's see. If you're not sure if you got it, let's look at it now.
you got to type in this stuff. I don't think it's wrong either. It's just showing a different viewpoint.
All right, so some more with this. We got our graph, but we're going to answer a few questions here. So I'm going to go ahead and erase what we got already. Graph up. Next thing, we're just going to figure out population after a certain amount of time. So first one, let's find population after 4 hours. Okay? So some question D along with this one. What is the population after 4 hours? So how are we going to figure that out? We're just going to plug 4 in for T and just plug it in your calculator. So we're going to figure out that what N of T4 is. That's going to equal 1,000 times E to the 0.01 times 4. And like I said, just to save yourself a little calculator work, instead of typing in 0.01 times 4, just type in 0.04. Gives you just less of a chance to make a mistake. So to the nearest bacteria, what do you get? What number? Yep. So we know after 4 hours now, that population went up by about 41. Seems kind of reasonable. 4 hours isn't that long. Went up by some, but not a crazy amount. Going the other way with it, this is going to use our own rules. Question D. When will the population be 1,700? When will the population be 1,700? N is your number. Right, N of T will be 1,700. Now what we don't know here is what? So we're going to solve for T. So I'm going to plug in 1,700 for N. So 1,700 equals 1,000 E to the 0.01 T. Now at this point, does that look familiar? What problem did we do earlier today that was exactly like this? Just different context. One of the homework problems we did. When it was continuously compounded. What? Yeah, I think that was right. I think that might have been here. It's just like that. Because something that's continuously compounded follows the uninhibited growth line. That's kind of cool. Bacteria growth works the same way as it does in some cases. So to solve this, what do we do first? Divide by 1,000. Do that on both sides. So we get 17 over 10, which we know is 1.7, equals E